Okay, sorry about that. All right, so we have a great panel here today. So we've heard from, I think, everyone today except for one. So we have Max Welling, who you heard about earlier this morning. George Dahl was unfortunately not able to give an invited speech due to some conflicts, but we have him here today. He's also worked on some interesting work related to message passing neural networks for quantum chemistry. So then Anatoly, we just heard from recently, and then Gilles Loup, Ian Murray, and then Juan, who we just also just heard from if you were here, hopefully. So it's a great honor to have you all here. Thank you very much for joining. The theme of this workshop is to bring together, obviously, the ideas of machine learning together with the physical sciences. And when we first were trying to think about conceptualizing this workshop, one of the points was that there's quite a bit of activity in machine learning for other kinds of sciences. So, for instance, in the social sciences and in health, you see a lot of that's going on. And one of the things that we were trying to kind of focus on and distinguish what's going on in the physical sciences is that if you compare that to something like health, you don't necessarily know what's going on. You have a lot of data. It's very difficult to tell the difference between the correlations in the data and the causal structures that are actually going on. And the causal problem, the causal inference is one of the very, very difficult problems in those areas. It's very interesting. But in contrast, in many physical sciences, the causal structure is actually much more clear. Not always, but oftentimes more clear. Often there's some kind of mechanistic model that's very well motivated that you understand, and oftentimes you also have simulators. And so there's a different kind of class of problems that you run into, and we didn't really see a forum for discussing that so much, and that's why we created this conference. And I think it's been a very successful. We've had a bunch of excellent posters. We had over 65 submissions showing that there's quite a bit of demand and interest in these activities. And so in this panel, basically, I'd just like to kind of drill a little bit deeper into some of these issues, so both in terms of this kind of convergence between the scientific areas of machine learning, some practical areas about collaboration and things like that, and then we'll just kind of see where it goes. So I've prepared a few questions, but we'll see how it goes. So, okay, so first of all, based on what we were just saying, and some of the last talk was also a perfect example, is that we often want to try to take some of this mechanistic understanding that we have about what's going on and being able and inject it into the machine learning algorithms if possible. Of course, there's some balance that needs to go on between these sort of assumptions that we're making, especially when you have noisy, maybe not very well understood noise models and things like that. So there's a two-way street of one, so I'd like to discuss how it is that we can go about trying to inject our understanding into the machine learning models. And then as a sort of follow-up, maybe we can talk about, after doing some sort of learning, how we can try to extract that information, and then maybe, and also touch on issues of interpretability, of how can we then use that as sort of scientists in a traditional way. So that's what I would like to kind of explore that topic for a little bit, if I can. So I don't know if anyone really wants to take it away with that. I can pick on someone if we want.
So yeah, that's definitely very interesting. Also, because in machine learning, typically we want to have these data-driven feed-forward models. We're all very excited about our deep neural nets. But I always am amazed if you start collaborating outside of this little shell that we live in. Basically, everybody is doing simulations. So simulations is a really great way to inject expert knowledge into your models. And there's economy, in healthcare, in astronomy. It's basically everywhere. And I think of it basically as I'm a bit biased because of the sort of variational autoencoder view of the world, but there is a generative model which has a whole bunch of advantages, which is one of them is injecting prior knowledge effectively, using causal relationships, being interpretable, being data efficient, being able to model the input distribution, which allows semi-supervised learning. There's a whole bunch of sort of advantages that you have by doing that. But then there's always variables that are noise variables, or latent variables, or parameters that you don't necessarily know, and you need to infer those. And then there is sort of these data-driven models or recognition models that look at the data and then try to get back at inferring distributions, posterior distributions over all of these quantities. I think there's a very nice kind of feedback loop between those two that I think could play out very nicely.
Exactly. So in those situations, in something like the VAE, usually the generative model is something that you know exactly, and it's maybe it's differentiable oftentimes and things like that. If you want to try to include these with the actual real scientific simulators, how does that change in terms of scalability or just all of the actual techniques?
I think that's a really interesting frontier to think about, and then that touches upon like approximate Bayesian inference or approximate Bayesian computation, which is a whole field of statistics. But there's many shades of gray, right? It's like you have a generative model that you can highly parameterize by the physics that you know, and you can slowly sort of relax some of these sort of prior assumptions and parameterize them and try to learn them from the data. Now, if you can't backpropagate through it, so the best situation would be if you backpropagate through all that, but sometimes in the simulator that's not really possible, although there's a lot of advances in actually improving on that too. But then the next step is to fit a surrogate model. So basically, you fit a model that really sort of imitates the generative model, which you can only run in the forward mode. And then there's now really recent excellent techniques, actually DisNIPs, like Rebar and Relax, that can help you fit at the same time these forward models, these surrogate models, and do inference. So I think there's a lot of progress in this. And I'm going to hand it to somebody else.
But is there enough progress to solve any real problems?
That's good.
I mean, it's very exciting to use VAEs, but it's not easy when you have a lot of discrete latent variables, or if you have maybe imperfect models or understanding that in themselves do not encode enough information. Just as a, if you want to respond.
Yeah, I have to respond. So I think there's good hope, right? For instance, in the morning, I talked about a model that was basically a realistic sort of forward model for, let's say, generating measurements from, let's say, from images of the sky, and then you're trying to invert that. So you can definitely think of that as sort of one generative direction. That is, in this case, you basically know it completely, or you can just have some variable or some parameters that you still want to infer, and then the backward direction is run as a recurrent neural net. So there's definitely problems that are already practical, in my opinion. With Google resources, you should, in principle, attack any other. If you have a simulator, you're in good shape, in my opinion, right? So I think yes.
It's mostly for rhetorical effect. I actually agree with some of these points, but I think there's no good workshop panel if everyone just agrees too easily. We need to spark controversy, I think. Ian wants to say something.
So I think it's useful to make a distinction between models where we have no, I don't think I did. I think it's useful to make a distinction between models where you have a deep mechanistic sort of understanding of this is the model that I want. I have this understanding that this is like fundamental standard model of physics, and this is how particles behave, or this is sort of a pretty close description of how the universe evolves, and that concrete model is what I want to do inference in, and it doesn't make sense to change it. Whereas sort of down the hall, a lot of people doing machine learning just want some generic, useful, flexible structure, and you can take inspiration from all this physics stuff, but because you've got all this choice in your latent representation, I think you don't want to inflict too much pain on yourself unnecessarily. So we're a bit prone to sort of doing things that are beautiful mathematically, but we can choose to do things that will also be easy mathematically and easy computationally, and still take advantage of the physical constraints that we're hearing like the last talk. So, for example, Neil Lawrence's group had nice work saying we want to get good kernels for Gaussian processes, and if we invent little fictitious physical systems with dashpots and dampers in them, that will give us a structure for kernels that we can learn. But it's very nice, tractable machinery. We're not literally thinking that this is a physical system with dashpots or capacitors or whatever it is that you're modeling. It's just a nice structure. And so some work in Yoshi Benjy's group, following on from work I did, there was this thing NAID-K, where it was like, here is a useful neural network. We will write down what mean field updates would do. Mean field updates would be this painful thing to do on a model for a restricted Boltzmann machine. Restricted Boltzmann machines are sort of nice, beautiful things, but hard to work with. We'll just write down what something sensible would do and then differentiate through it, and then treat that as our model and throw away the original restricted Boltzmann machine because there was no fundamental reason to use it anyway. So I think that sort of one direction here is we can say, we can look around physics and we can say, is there like some tensor network thing that we can steal and then differentiate it and use it ignoring the original physics? And then there are other cases where it's like, okay, now we can't change the generative model, we're stuck with it, and that's harder.
So I think another interesting approach is to rather make the neural network use of our knowledge or simulation and to force to use the network to use the simulation. So for example, what I presented this morning. But another way could be, for example, probabilistic programming inference, where you are really forcing the network to go through your code and then to use it to make good predictions. And I think this is a really interesting approach to force the network to use that knowledge. And also, if, for example, you have a probabilistic programming inference engine, you can also then use that, then, for example, to sample the posterior, or some, for example, some very rare observation that you get from nature, and then just sample from the posterior of the traces of the program to then understand the story that led to this observation. And I think for the scientists, this is could be very insightful.
No, I agree. Maybe I'll come back to that point again in a little bit.
So my take on this is that it hinges a little bit on what you define to be a problem. Of course, various flavors to what people think is the most pressing kind of problem. Now, in terms of science, what natural science want to accomplish is to gain a deeper understanding of how nature works. So, to succeed, for instance, in getting a nice Chorovet model or even a great neural network that works in all the possible prediction validation tests, that is certainly necessary, but not a sufficient one. And you want to open up that model and see if there's something in there which you can extract and then possibly apply to a truly extrapolation case. And so to me, maybe the challenge we are fighting with is how would you properly define such an extrapolation regime? Okay, is there a general rule about that?
Yeah, I think that also gets at a little bit what I was trying to probe in terms of extracting information. So one is being able to inject information into the models, either in terms of using a simulator with this kind of forward-backward VAE story. You can also try to incorporate understanding into the surrogate models or the networks themselves, like you were doing with the many-body systems, or what you were suggesting with the tensor networks, and somehow trying to take some physics that you know and inject it. But then after you've done something, you'd also like to be able to extract from that something that you can use to generalize, perhaps to create a new hypothesis, or in some sense a very high-level form of transfer learning, right? You've worked on this problem, you learned something, and you're going to take it to some very different domain where you maybe have no clear way of being able to transfer that knowledge in any kind of neural network-ish way. So I think that's what you're getting at, and I think it's, I was hoping we would get to this, and we got to it very quickly, is that, you know, we've had this, there was this symposium about interpretability, and I think people worry about, for instance, you know, why the car decided to do what it did and various kinds of auditing, but in science there's another reason for interpretability, which is maybe not that it just does well on this particular task, but that you somehow have this quest for deeper understanding, and but trying to formalize what exactly it is that we want, like what kind of interpretability and why is it that we want you know, something other than this black box, and like how are you going to use it is interesting to try to kind of quantify. And I think you started down that road in terms of this deeper understanding, but it's sometimes a little bit challenging to quantify exactly what it is that you want to do. I don't know, Juan, do you want to comment on this at all?
So in our experience, yes, is what you said, that there are different levels, right? Like, so we derive a bunch of models based on neural networks, and we were able to, for instance, get to the bottom of like what they learn. But so that's the simplest level. But one thing that we found really hard is why is it that gradient descent or stochastic gradient descent does that? So I think that's a pretty important question, and we don't know in physics. I don't know how this question is understood in machine learning.
So I think the best place for machine learning to help physics, for instance, is basically solving computational problems. So for instance, a surrogate function. So there's a project that I've done with John Frankelbatoni, who's a physicist in Amsterdam. And so they're basically looking for parameters of a supersymmetry model that could explain sort of the data, which sort of deviates from standard model predictions. And in order to do that, you have to sort of run an MCMC sampler in parameter space. But in order to do that, you have to run these forward simulations all the time. So it's way too expensive. So basically what we did is we ran we learned a sort of Gaussian process surrogate model, and that would be able to take over the simulations whenever it felt confident that it could do it. So the GP basically would produce predictions, and if it was confident, you wouldn't have to run the simulation. And if it was uncertain, you would have to go back to the simulator and then run the simulator, the data would be used again to update your GP. So everything is interpretable because you know your SUSY model, you know your standard model, but the machine learning came in to basically help overcome the computational burden of running these forward simulators.
Yeah, I think that's a really nice example, and it reminds me that I think a lot of the time when machine learning methods are being used, and I've seen them, no one cares about interpretability. It's just a cheap surrogate from some function which is already well understood. And the dangerous thing with most neural networks is that they don't have some mechanism that screams at you to say, by the way, this input that you've just given me is totally weird. It's like not like anything I've seen. What I'm about to output is total junk. And Gaussian processes sort of are this nice, beautiful way of dealing with it. But as people are getting more ambitious, they're using deep neural networks that might come with some of the Bayesian machinery, but not necessarily sort of trustable. So, I mean, we see with adversarial examples that you can tweak inputs a tiny amount. They'd be a tiny square distance away from an input. A GP would be fine with that. They'd be like, oh yeah, it's good. But the output is junk. And we really need sort of robust mechanisms to sort of diagnose that sort of problem.
Yeah, no, I think, I mean, so definitely I think that this idea of using machine learning to ease computational burden is a very clear direction that can be used, and there's a lot that can be done. I think there are examples where you could try to go beyond that and try to extract something. So when we were hearing about the genome-wide association studies, that's in some sense the farthest afield from the physical sciences, because that's more, again, to where you don't know the causal structure. And there, kind of the beauty is that through this process, you actually learn the causal structure, and then you're extracting something you didn't know. So it's a deeper level of kind of discovery than you expected. As another kind of just example to try to, spark some discussion is, I just started collaborating with some people doing something similar with these lattice type of approaches, and the networks were learning something we didn't understand what it was, and it looked like it was actually latching onto some topological property, which is interesting, especially since physicists didn't really know about these very much until fairly recently. So like the idea that these networks might actually discover something that we don't know about is pretty exciting, right? So, and you can imagine using a simulator, for instance, the Ising model, and not having had the theory that told you about the critical points and things, and maybe somehow having some story like that. So I think it is exciting to try to think in that direction. Of course, that would be like the ultimate, I mean, it's a higher level of machine learning, but how we get there is a challenge, and how you can, and that's also one of the reasons it'd be nice to be able to interpret in some way, but having the language, so Gaussian process kernels has kind of this nice thing because they're a more natural language to encode some physical knowledge, and neural networks is oftentimes more difficult to find the language. So I guess maybe, I don't know, the question is, should we be looking for some way in the kind of deep learning paradigm to be able to, do you think there's some way that we could come up with something that's like the Gaussian process kernel, where it's like a nicer language to encode some physics knowledge, but it still looks more like a deep learning approach?
So maybe I reject the premise of the question. I don't see why we need to use deep learning for everything. We can use GPs when they're appropriate, but it feels like there's this huge number of problems where we don't need that sort of low-hanging fruit that haven't been solved yet. So maybe we should just do all the easy things for a while until we run out of easy things to do. And then Ian and Max can think really hard and come up with the next thing. But all do the easy stuff. And there are a lot of cases where the output of the model is something with units, like if I produce an energy, like you can interpret an energy, right? And so the outputs themselves can be interpretable because they're trained to be interpretable. They're trained to mean the thing they're supposed to mean. That's the whole optimization problem that we solve. And I think we should keep using sophisticated Bayesian models and integrating out their parameters and reasoning about them very carefully and getting very good priors that are based on our knowledge of the world. And we don't need to stick a neural net in there if that's working fine, maybe.
I wanted to say this is almost a philosophical question that you're asking, because so if you do pattern matching, so you have some very complicated data and you're trying to find patterns, right? So humans like rules. So we find a rule or a very simple differential equation, we get happy, and then that's a physical law, right? But there could be selection bias. It could be that we have discovered all the simple stuff, right? But that in fact only the complicated stuff is still left over for us to discover. And the only way to properly describe it is by, a neural net, but not really with language, or maybe with a very complicated set of equations. And so, is there maybe a time that we have to go beyond human understanding, right? Is there maybe a time that the only thing, the human brain in some sense is like that, so maybe we will never understand the human brain, but perhaps we can simulate one, right? But then do we understand it, or do we care? I don't know.
Right. No, it's definitely a philosophical question in some sense, but I think it's kind of interesting because the physics and the physical sciences and machine learning, that's kind of what's interesting about this hybrid is you get to kind of attack these philosophical questions, but with a little bit more meat. You have some specific scientific goals, and also certainly in the particle physics case, it's a little bit of both. The fundamental interactions we have some nice theory for, but the detectors are horribly complicated, and we're not looking for a theory for how the detector really works. So having some hybrids of these two that are able to describe the data well, where we can still extract some nuggets and some theoretical formalism or something is very valuable. For you?
So I agree that there's this philosophical component to this. And in one of my quantum mechanics professors, he used to say you didn't really understand a molecule unless you can predict its properties quantitatively. And so a good simulator, where we don't know how it works, it does that, would then qualify for such a definition. I don't know. He of course was referring to proper quantum mechanics doing that. So I don't know if that's. I would again agree that this is a necessary condition for understanding, but is it sufficient? I don't know.
So I'd like to say that you can approach this in a more practical level, right? Like you get your result and you try to create as many diagnostics as you can, and see where you go.
Right.
They're very hard to interpret, like the models, the wave functions in quantum mechanics and so on. But we still get a big bunch of meaningful numbers out of them, and we use them and we like. So I think we should aim toward diagnostics that we can understand.
Excellent. So maybe we can pivot then from the kind of philosophical side to a more practical side, and the also referring to quantum mechanics, going from the philosophical debates about the interpretation of quantum mechanics to the shut up and calculate attitude. If we have these models, and maybe you can or cannot interpret them, but they're describing the data well, one thing that we didn't talk a lot about during this workshop, we talked a lot about trying to do inference from the data, but we alluded to it a little bit at the beginning as trying to use these to plan the next set of experiments. So maybe we can talk a little bit about experimental design. And I'll start off actually with a question I wanted to ask you on, which was when you do these mini-bottom quantum states, and you can say that the system has done a good job of representing it, and you showed that this entanglement entropy, which is something that's very difficult to measure, at least when you look at it, it looks like it's doing a pretty good job. Can you use the model to then try to guide some new kind of observation or new kind of measurement that might be efficient and actually being able to measure this quantum entanglement, or does it suggest new experiments that you can be doing?
That's a tough question. I guess yes. I just don't have precise example right now.
Mm-hmm.
But you can imagine like getting so entanglement, like it characterizes a big bunch of different things for quantum systems. So if you get to that point and you get to see some suggested characteristic in the entanglement, then you can say, okay, I'm going to focus on this now that I've got the state in a different region. So I guess again.
Jules, I don't know, you've worked in this direction, do you know?
So yeah, I think definitely machine learning can help in this domain, and it goes back, I think, to the computational comment that you made. Is that in this use case, and for that, machine learning is really then helpful as an optimization algorithm, basically, to guide what should be the next experiment that you need to do. But then again, to answer this question, you need an accurate engine and an inference engine to actually simulate what would be the information gain that you obtain, maybe in expectation, by doing this experiment. And so this is itself a very difficult problem. And then you need to search over the space. And so it means that you need to be able to simulate all the experiments that you could do. And so there you need some really deep human knowledge about how you parameterize your experiments. And so if you have many parameters to search, it's really difficult because every evaluation is very costly, and you want to optimize over a very hard parameter space. So
Right. Yeah. So I'm curious, to what extent the developments we're seeing in reinforcement learning, or also with meta learning, can then start to come into play, because here you really have it's basically an optimization problem, and also computational constraints become really key. I don't know if anyone else wants to know.
I think there's developments in machine learning that sort of address this, and could potentially be applied, that go under the name Bayesian optimization. So if the function you're trying to search over is reasonably sort of smooth, then this might have a chance of succeeding. So your comment this morning in my talk about where to place antennas, could be a very interesting one. Optimize using Bayesian optimization, or maybe reinforcement learning is possible, maybe. That's,
So I think there's to experiments that there are also many sort of angles and the experimental design and in chemistry where you would try to identify the optimal reaction conditions or the best catalysts and so on. It's pretty straightforward. It's basically an optimization. I think that's clear how to do this. Now other sort of experiments which rather would go to increase our understanding. So, for instance, thought experiments or something like that. I feel less confident, or it's less obvious to me how or if that's possible. Just as an example, when I give my introductory course in quantum mechanics, we discuss perturbation theory, which is basically just Taylor expanding in your Hilbert space. And so would this sort of thought experiment, let's construct this Taylor series and let's look at each term as a function of order and extract the underlying patterns, how they evolve for each order. I think that's to do this thought experiment it's more demanding or more challenging.
So, okay, so anyone else? No? Okay.
I guess a quick comment that in the collaborations I've had, there are sort of two things where you could decide what to do. Some sciences spend vast amounts of money on simulations as well as massive detectors and equipment. And if you're guiding what to do in the simulations, it's all inside the computer. It's much easier for the computer science collaborators to sort of get in on that loop. Whereas if you're trying to tell them where to place equipment or how to place together to put something before it's like glued or drilled into the detector, you have to be involved years in advance and really embedded in the project, and it's sort of quite a harder job to enter in that.
Right. No, I agree. I mean, I think there's both the kind of the design in terms of like the actual experiment, and sometimes also in terms of efficiently using the simulator. In terms of the learning process itself, you can use the simulator in a more kind of more clever way. So maybe we can talk a little bit about collaborations now, since we just started in that direction. So I'm curious both about the kind of some practical aspects of it and sociological aspects of it. But maybe before doing that, we can talk about just specifically one common way that people try to collaborate between some domain and say machine learning, computer sciences, is through some form of a challenge or something like that. And oftentimes, and now we're seeing also move more and more towards open data, which will certainly help things. I'm curious, one, about your attitudes about challenges, and the other one is that, especially for the physical sciences, I've had this feeling that the right way of communicating is maybe not big data sets, which is easy to start with, but to actually try to provide the simulators themselves so that people can generate data on the fly and investigate all sorts of interesting directions. So I'm curious if anyone has thoughts about pitfalls or the great things about challenges or open data simulators, these things.
So I could give an anecdote about a challenge, because there was one I entered. There was a Kaggle competition about weak lensing, and came second place as first loser. Tim Solomon, who's in this community, came first, and I learned a lot, and it was great as a way of getting people in who wouldn't normally talk about it to do this challenge. So that was sort of the first thing. I know a lot more about weak lensing than I did before. And the thing that I think is not so useful is like the log of code that either I or Tim submitted to claim our money. When you set up a challenge, you have to make it so a leaderboard can be computed. You have to slice out some small part of your problem and maybe score it in a way that isn't exactly what you care about. And so I doubt that any of them literally ran our code and used it. But what they did get was a write-up where I know at least I wrote an essay saying this is what I would actually do end to end in this problem. So it got people in to sort of think about the whole problem. So I think it's very few people really need some people to grunt for free on a classifier, but if you are able to carve out something interesting that just gets people thinking about it, it's probably the collaborations years down the road that would be most useful. And it's a lot, yeah, Kaggle competition is a lot of fun. I think worth setting up.
So I think competitions can be very valuable, but also even getting benchmark data sets, but we need kind of two things to get it to take off. You need some cottage industry in the machine learning community to show that one of its ideas is worthwhile. And then you need a data set that's very accessible. So Anatol collaborated with me and some of my colleagues, and it was, now there are other colleagues of mine in other labs that are coming to the problem from a machine learning standpoint where they want to compare to the models that we used. And so now they want to run on the same data. And they're probably going to get good results because they're going to put their comparison in. It's almost certainly going to be better, right? So this is the sort of way you get this sort of follow-on value from a collaboration if you make the data very accessible and easy to use, and maybe, you know, if you're measuring the wrong thing, you'll have a whole community reporting results on a problem that you started that ends up being useless. But maybe not, so there's still hope. But one other thing I'd like to say about starting collaborations is, like, there's nothing like just cold emailing someone and offering to collaborate. It's a little risky, I admit, but my colleague Chris Chalou emailed an astronomer after reading about their work in like a magazine or something, and did a really exciting collaboration on Kepler data. And there's a press conference by NASA on the 14th, so in about a week or so, if you're more interested in that. But this all started from just him, I guess, being bored at work in the office. I don't know, maybe not. Being very busy in the office, but knowing that he could be even busier, and emailing someone because he was interested in learning more about astronomy. And I thought the collaboration was very successful, but this can, I mean, we need more of this type of stuff.
It's a shock to me that there are machine learning people that are afraid to write to physicists or scientists to see if they want help. I think, yeah, email, please. We need your help.
So just sort of inspired by the open data. So of course, it's like great to have open data, which physical sciences is better at. I think there are sciences where they see their data as their proprietary source of advantage and they hold on to it. But that's not enough. Like the whole Sloan Digital Sky Survey, like an amazing resource. It's free on the internet for anyone to download off the server if they knew where it was. But that's no use to me. I wouldn't know what to do with it. You have to have a collaborator that can sort of say, here is the standard pipeline that we would use to get started. Here are the sort of ways to look at it and questions. And one of the things Kaggle does is forces the people who are setting up a competition to work out how to frame some window onto a data set to give a quiz problem that people have an entry point to, and that's really important. Even if it's not exactly the problem you're interested in, just something that gets people playing with it is important.
Yeah. So I agree with all that. I think it's always very valuable for the participants of the challenges, but for the organizers, for the science, I think the conclusions are not the same. I mean, because usually if you want to solve a scientific problem and you're asking for help, it means that it is very complicated, and so you will not be able to simplify it into a Kaggle competition. There will always be some details that you will need to leave out, and what then you get at the end of the competition may not much align with your actual interests. So, and then you may try to then incorporate more rules into the challenge. So this is what happens, for example, for the second physics challenge on Kaggle, the Flavor challenge. But then it can still be difficult to set up in the correct ways. It's just that you can, some participants like myself, you can even crack the rules of the game such that you actually win the challenge, but because you found a loophole in the rules, and then we don't get any science done by doing that. We just play by the rules, and so it's a difficult thing to do.
I agree.
So I think that the role of collaborations can hardly be overstated, at least from my perspective, in pushing the field. How my group or my research has changed after collaborating with people from all sorts of backgrounds, but most importantly, this kind of applied math and computer science. It was fundamental. So I organized a program in 2011 at Institute of Pure and Applied Mathematics at UCLA. And this is where I met Klaus-Robert Müller from TU Berlin and other machine learning scientists. And that's really what started. So it wasn't a chemistry institute or chemistry conference. It was actually a collaborative setting. And so these kind of interactions continue. And as George mentioned, I always think, or my experience is that always both sides learn tremendous thing of insight, tremendous amounts of insight. And so I can't see any negative of that.
Yeah, no, I think it's so. I think probably everyone agrees that these collaborations are very valuable. The difficulty is, of course, then starting them, and then there are oftentimes there are barriers. And certainly, in my field where there's very large collaborations, there's a lot of inertia and difficulties in politics and things like that. So what are some of the biggest barriers that you see to forming these collaborations, and what kinds of things do you think we could be doing to improve it? And what could we do to try to bring more machine learning people into the kind of physical sciences area to try to incentivize it as that, as opposed to, and there's some areas that have really a tremendous amount of activity. And I mean, while this is a good turnout, it's certainly not what it could be, right? So so what do you think we could do to try to improve that? Please.
So I like quantum mechanics, right? And that's what I do. But I think it could be taught differently, in a more accessible way to people in math and computer science. So I think that would help with that. And I think there are ways to teach quantum mechanics in a more accessible way.
So pedagogy is basically true. Yeah. It's certainly true that when I try to bring people in, they often ask, can you point me to some kind of review article to get started? And I'm like, well, I can point you to the entire literature of particle physics, but that's not going to be very, useful. So we're definitely lacking a lot of kind of entry level, onboarding material. I think that's certainly one problem. I agree.
So I think there's definitely barriers in the sense of if you write a paper on the interface between two disciplines, then for the computer science people, it's not cool enough, right? It's not the latest deep neural net or whatever. And for the other community, there's sometimes also skepsis. And so on both sides, it might not be state of the art or what everybody's excited about. And that actually makes it sometimes really hard to either get it published or get funding for such activities. And so I think making the funding agencies aware of this problem is a good step. But this is really where a lot of really interesting things happen. And the other thing I wanted to say that I've noticed that there's actually quite big danger if you start a collaboration. So you start all sort of excited, and then it drops dead at some point because people get too busy, so you need an enormous amount of dedication to keep going because you have to get over the barrier of learning each other's language. Well, you also have 10 other things that you need to do. And so you really have to find a problem that that can only be solved on this interface, and that everybody, you have to agree what it means to have success, and that everybody is extremely excited if you make it to that point. Right? And so I think often these things drop dead, which worries me.
I completely agree with that, but I think that machine learning can have a really big impact on problems that aren't on the cutting edge of the interface, where lots of people have problems that would be solved by totally standard things. And I think we need to think of mechanisms to make that happen. I'm a strong believer in teaching, but maybe you need to have people who are passionate about just doing really good engineering of existing solutions. So I know one of the British funding agencies, EPSEC, has sort of recently recognized that a lot of fields need really good software engineers on hand, and they sort of got paid for software engineering fellows to sort of get better software practice in sciences. And I think we need the same sort of thing for general data science, including machine learning, where some people will really enjoy just doing a really good job of applying standard stuff and occasionally doing the new thing when it's needed, or bringing in people to develop the new things. But I think we're a bit negligent if we talk to people and go, well, your problem sounds kind of boring, so I'm only going to do things where I'm going to get a next paper because I can add some new bell or whistle onto the model.
Yeah, no, I definitely agree. The incentives around around academic practice, and this is really an issue in both largely in academia, but everywhere, to be able to value these contributions that are in terms of software and data and the research software engineers and things like that. Actually, so one of our sponsors for this is the Moore Foundation, and the Moore and Sloan Foundations have invested heavily into trying to change the culture, at least in U.S. academia, to try to incentivize these things and change this problem that is definitely an issue.
So I have an anecdote of a recent paper we published. We got resistance from referees who sort of questioned the whole reason of applying machine learning to quantum mechanics. One of the referees asked this question: okay, would you trust your fit more than your postulates of quantum mechanics? and so I think you can argue against that, but I think the most powerful argument in the end was that you had results which otherwise you wouldn't have gotten. So in the end, that's, I think, the most convincing. And there's definitely, I think, a major role in meeting this resistance and arguing against it and demonstrating that you get faster to better results. So that's a lot of legwork, I think, but I also think it's worth it.
Okay, well, maybe that's a nice note to end on. So I don't know if this is my first time we're doing this kind of moderation. We didn't really leave a lot of time for questions. Maybe I should swing it out to the crowd here for a little bit. Does anyone have any burning questions they would like to ask the panel before we kind of great.
So an ongoing problem I have with people, or collaborating with people who build simulators, is they're very used to modeling very exquisite mechanistic detail in their simulators. And when I propose some kind of surrogate model where they lose that understanding of all the features and all that prior knowledge, it can be a bit difficult to convince them that it's trustworthy. Could you expand a bit on your experiences of dealing with collaborators who build simulators and how you approach that problem?
Can you repeat the question?
Yeah.
Maybe someone on the panel.
Sure.
Yeah, so I think the question was that collaborations between people who build simulators versus people who try to build surrogates for those simulators don't always trust each other. So, and so I've been lucky enough to collaborate with people who actually really wanted to trust that. But I think the most important reason for that is that there was a task downstream. So it wasn't really about the simulator. It was about speeding up a search problem through a space of parameters. And if you can show that you can do that better and more efficiently. In some sense, it's a black box, and who cares, how you do it, right? And so, I guess in that case, focusing on the downstream tasks is maybe important at that point.
This came up in at least one of the talks that the obvious thing to do is to have sort of held out data and check and match there, and then the obvious concern is how is this surrogate model going to be used downstream? Could the distribution over input shift on you? And it comes back to the same issue of whether there's anything in the system that's diagnosing uncertainty, and a small control space that sort of trusts GPs to do something sensible to flag when you should go back. And in big control spaces, I think it's a real concern. I think we don't have enough research on that area, like how to flag this is scary. And I think that's a really good question.
Other questions from the audience? No? Going once? Okay, yep. Oh, look at that.
So in these physics problems, a lot of times you're using these simulators to build a big neural network to do inference. And then you want to apply that model to actual data from your big, expensive detector. If the distributions don't match, like Ian was saying, we need to detect this and flag it. If it doesn't match exactly, are there techniques like from transfer learning that we can use to try and adapt to this situation?
It's a tough one.
I think there are ideas, but like you can patch your imperfect simulation or to try to correct for the misspecification that you produce. Like you can generate data which is imperfect to some point, and then maybe you can push the data to another network, to a first network, to try to correct and to produce data which is more aligned with what you have. But this is just an idea. I don't think anybody actually try that. I'm not sure.
I mean, I think one answer is there isn't a short answer to how to deal with what goes wrong. I mean, it depends on the system. If the thing you're modeling is a model of all of your complicated sensors, as Carl was saying, you might not care about, but they're there, they might be drifting over time, and it could be that the system's changing over time, or it could be that it's just your input distribution that's changing and the outputs aren't. So you've got to think quite hard about the problem, about what things might drift before working out how to deal with it. Amos Storkey has quite a nice review article on data set shifts of different sorts, and he sort of enumerates the different sorts of things that could happen. So even if it doesn't have solutions, I think that's the first step, to sort of reason about the different things that could be going on.
I just want to say there is a field called domain adaptation. I'm not sure that would fit precisely for your problem, but there is a lot of papers being written on this problem, which to reweight certain things in order to try to shift input distribution. But anyway,
I mean, in the particle physics situation, since we know that our simulators aren't perfect, even though they're fairly, very, very detailed, we've developed a lot of heuristic ad hoc kinds of ways to deal with it, but usually where the statistical analysis is still in comparison, simple. And so once you stick machine learning in it, it's more complicated, but we can borrow a fair number of those kind of heuristic approaches. But a lot of times what we do there is you're taking the simulator and you're kind of expanding the model into a bigger family of models. And then that's exactly, we take a domain adaptation idea. And so the family of generative models is now parameterized with nuisance parameters, and then we try to be robust to that parametric family. And that's exactly what Jill was presenting with this learning to pivot. So that's one approach. Of course, it's only going to be robust up into the family of this expanded simulator, right? You had the original simulator, and now you have an expanded simulator with more knobs. But you're just always going to be able to kick that can down the road in terms of, so you cover the bases of the known unknowns, but then there are the unknown unknowns. And that's a very fundamental question of science that you're never really going to get away from. Sorry. Okay, any other things? Okay, well, if not, let's thank the panel. And I'll just say a few final words. So again, I'd like to thank our sponsors, so Intel Nirvana and Cray and the Moore Foundation. And I'd like to thank the reviewers that went through all of the presentations, the poster presenters for making beautiful posters, the presenters, and then all of the organizers for putting this together. And I think it's been a very successful first workshop. And we are planning on somehow continuing this series. Exactly in which format and which place and what the title will be is kind of up for discussion. But thank you very much. Okay, and have a good night.